So now we have a suggested metric for assessing the correctness of spot detection and matching. We're summarizing this in one parameter called combined correctness. But the key question then becomes, is this a useful indicator of a successful 2D gel image analysis? Meaning, does this mean, does this correlate to a correct and complete results? Will it increase the number of true positives? It will decrease the ratio of false positives? Well, to answer that question, we set up a study together with 5 proteomics labs around the world. And what we did here, in a few short words, were to run a large number of projects twice. And each analysis of each of these projects was evaluated for its combined correctness, the number of true positives, remember in image analysis terminology, and the ratio of false positives, also in image analysis terminology. And then we plotted the results and looked for correlation to see if we could find any. So first we plotted the combined correctness measurements of these 11 projects with 22 analysis versus the ratio of false positives in the results. And there was very clear correlation that the higher the combined correctness in the image analysis, the lower the false positive ratio in the results. Plotted in another way, you could say that for each gel set we had 2 data points. I've analyzed twice. We had 2 measurements of combined correctness, we had 2 measurements of false positives. So we could relate those, and we could then plot this arrow plot where we mean that when the combined correctness was higher, for the project where combined correctness was higher, the false positive ratio was lower for gel set 1. The same for gel set 2, and for all the gel sets. Every time the combined correctness was higher, the false positive ratio was lower, without exception. So it's a very strong correlation. The second question is how it is related to the true positives. And again, we plotted, we had 2 data points for each project since we analyzed twice. We had 2 measurements of combined correctness for that project, and we have 2 measurements of true positives for that project. Now we put all these data points in the graph. On the x-axis we have combined correctness, and on the y-axis we have the number of true positives that was found in that particular gel set. And every time when you had a higher value of combined correctness, you also had a higher value of true positives, without exception. And this could also be plotted as an arrow plot. Every time the combined correctness was higher, the true positives were also higher for all the gel sets, without exception. So the answer to the question if it's a relevant and useful metric is yes. Higher combined correctness was clearly correlated to a higher number of true positives, meaning potentially more biologically interesting findings, and a lower ratio of false positives, meaning less noise in the results. So the question then is, okay, we have a metric that seems to be really relevant in terms of how it can improve your results, but how could the John Q scientist use this in his everyday lab life? How can he apply that when he's doing his 2D gel image analysis? We realized quite quickly that we have to develop a software that can allow people to do this type of assessment. So we wanted to create a piece of software that allows to do this assessment in a fast and reliable way. And it should also be independent of the image analysis software package that was used to produce the data. We did not want this to be just a Ludesi thing that you can only use with the Ludesi Redfin software. We wanted this to have a wider reach on the community because we really believe that this can increase and improve the overall level and outcome from this technology. So we wanted it to be compatible with all the major software packages on the market. Thirdly, we wanted it to be free, so everybody can use it without having to think about it. And the fourth factor is it has to be easy to use. And this resulted in Gel IQ. And we were happy to release Gel IQ, I think it was about half a year ago or something like that. So that is now a software that can be downloaded from our website and used for free to do an assessment of the data that you produced, independent of what software you used to produce that data. And that kind of concludes the first part of this webinar, which is answering the question why. I'm hoping that I can show to you that image analysis errors will translate and create suboptimal results, and that the approach of using reproducibility as a descriptor of image analysis quality is not appropriate. But there is another metric that can be used, and there is a software that you can use to do the assessment using this type of metric. So the second part will be focusing on exactly how this can be done. So we're going to show you step by step how you go through this process, and then ending up with a suggested workflow. How you can incorporate this into your overall image analysis workflow. So again, the GelIQ allows you to do this, but you first, of course, have to download it. And we have made this available for download from our website, ludesi.com/freetools/GelIQ. So it's ludesi.com/freetools/GelIQ. We are going to send you this presentation afterwards, so if you don't have a pen right now, you can pull this URL off the presentation later on. But when you have, let's see here now, the next step is, of course, to import the data from the data file from the software that you use to produce the image analysis data. And here I'm going to switch over to some screenshots from GelIQ instead of using this presentation, so just bear with me for a second. I think this should be the one. This is what it looks like when you open up GelIQ. It's a welcoming page where you are asked if you just want to try the software on a demo project or if you want to do it on your own data from an external project. And when you do that, then the first step is to choose what software that you use to produce the data. And as you see, we have made GelIQ work with the major software packages: Decider, ImageMaster, Investigator, Redfin, Melanie, PDQuest, Foretics, Protein Weaver, Progenesis, SameSpots, and so on. So you select the software package that you use to produce the image analysis data, and then the next step is to actually select the data file from your hard drive. But there will also be a little sentence here in italics that will be specific for the software package that you chose. So it will be an instruction for how you export the data from that particular software. So here from Redfin it says, from the start page, click the export button of the project. Select raw data including images, blah, blah, blah. If you select a different software, there will be a different instruction, giving you a one-sentence instruction on how to export data from that particular software package. When you've done that, you click the Please Select Data File. That opens up a browser window that you recognize from other computer environments. And you basically browse to the place on your hard drive where you have the zip file with all the data and the images. You select that, and you click Open. And that will then take you to the import process of the data. And when you click Import, you will also be shown an overview of the steps that you will go through during the actual assessment. So this works in 3 steps. The first step, listed here, is that you will be presented with a random gel region from a random gel in your gel set. And it will be blank. You will not see any spots, matches, or quantities on this gel region. It will be blank. It will ask you to mark all the spots you see. And this is a step we have to go through in order to be able to catch missing spots. So we don't want to bias your evaluation by showing the spots in this stage, because you want you to assess what are the spots, and then that's going to be compared to the spots that were detected with software. And by that procedure, we can determine eventually missing spots. And when that is done, you will be taken to the next step of the evaluation process, which is basically evaluating the spots if they are correctly detected. So you will be presented with one spot at a time, like this here, and you have one decision to make. Is this spot correctly detected or not? Meaning, is the spot outline encompassing the spot body, or is it not? So that's the only decision you have to make, one spot at a time.